Good morning, physics friends. Welcome to my kitchen table. The purpose of this video is to walk you through problem set number 1, which will enhance what we covered before we parted ways. This is the first magnetic field problem set, which would be using the right-hand rule for fields to determine direction, and then also using B equals mu naught I over 2 pi d to figure out intensity. So not that I'm not projecting this screen so you can actually read what's going on, because you can do this on your own. You can do this on your own computer, but this is more just to prompt you and show you, just show you what problems we're working on and so on. All right. Anyways, here we go. I'm just going to give you a quick walkthrough. I am not going to go details because that's for you to figure out, but I'm just going to point you in the right direction. This one is B field around a wire. We've seen this in class many ways. Either the exact geometry or either the exact geometry or something similar. This one should be pretty easy for you. Right-hand rule. Given the direction of the B field, looks like it goes counterclockwise around the wire. You can figure out the direction of the current. Same thing here, except we're looking at it not as the wire is shooting right towards us, but the wire is vertical, and it looks like to the right we've got dots, so you should know that's watch out, the arrow's coming towards you, and to the left it looks like very faint X's, so the field is pointing inward. Use your right-hand rule for magnetic fields. If you're not sure about the right-hand rule for magnetic fields, go back to the PowerPoint notes that we went over in class. Here, geometry getting a little funky. Okay, it's still conceptual, even though there's some numbers there. At point 1, it looks like you have one wire influencing the field at point 1. I think that L wire up in the top right is basically out of the picture. All right, wire 2 is surrounded. Above it, you've got, point 2 in space. You've got the wire, the current carrying wire above it rightward, current beneath point 2 leftward. You say, oh, well, a rightward current and a leftward current, they cancel out. However, you are below the rightward current and above the leftward current. So you have to do right-hand rule for both of those currents, and you'll figure out the B field that results. It's interesting pattern. So this is how a lot of these go. And again, we've covered the content. This is another good one. We've covered the content in class. Of course, it's one thing to sit and get, and it's another, which is what you do in class, and it's another thing to do. So, hence we go over it. All right, I'm going to try to keep cranking here. Try to keep this whole thing to a reasonable time. All right, wire 1 is affected by, point 1, they say it looks like dot inward, okay? All right. So, I'm not sure which way is the current. I think we have to... Do we figure that? Point equally distance, and wires not immediately don't affect. Okay, so a wire's not immediately adjacent to a point do not affect the magnetic field. That's important. I don't understand how we get in numbers. Oh, okay, at point 1, it's 22 millitesla, and it's a dot, so I'm thinking that it's an outward field. So it's looking like the current is rightward. Guys, correct me if I'm wrong on that. Okay, at point 2, look very carefully how that wire loops. So you've got a first pass, it's a right, and then the next pass, it's also a right because of the way it loops. So will those currents add up and double the field at 2, or will they cancel the field? Will their effects cancel each other out and make the field at 2, 0? At 3, you have 2 currents underneath point 3, and 1 current's rightward, 1 current's leftward. Okay, you start to get a feel now for some of these problems. We're, what, five problems in? We're 5 minutes in, and a lot of that time was me blabbing and not solving. So, okay, Numbers, 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 numbers. You got a single, okay. Ooh, all right. So I wouldn't worry too much about this one. We have a single moving charge, and we have a point in space at the position of the dot. Yeah, we got a point in space that's not directly above. So this is where you have to think like the vector cross product, the torque issue. When you open or close a door, you got to have a component that's your tug. A component of your tug has to be perpendicular to the door itself, to the moment arm. Otherwise, the door ain't going to move. All right. Same thing here. If that charge were directly under the point in question, we'd have like a maximum effect. Okay? But it's at a funky angle. So this is where you're going to use the law of Biot-Savart. It is going to be plug and chug. There will be sign of an angle in there. Rarely do you have to do this, but it is fundamental to what we're doing, so I put it on there. Okay? My apologies. But find the equation. It's in our PowerPoint. It's also in the book. That's where I get those PowerPoint slides from. All right. So see here you're going to use Biot-Savart, but in a conceptual sense. So the point in question, all right, so I am moving away from it. I'm not perpendicular to that point in question, but my velocity vector is not parallel to what I'm going to call the moment arm, even though it's not really a moment arm. The displacement or the position between the dot and me, there's a line segment there, okay? That line segment is not perpendicular to the velocity vector, which would yield max field, but nor is it parallel, which would yield no field. So you got to do, I don't know if that's 45 degrees. You got to do a little geometry there with all the 1 centimeters. So this is more common on, say, the AP exam. Even though it's not common, it's going to be more common than the actual numbers. You have to understand the law of Biot-Savart and understand, yeah, there will be a field. Actually, no, they want you to plug and chug on this one too. So it's just the magnetic field equals some function of the given stuff in the problem. You can find it right in the PowerPoint we did. Okay, now we're into B equals mu naught I over 2 pi r. Interesting in the algebra, and you'll see this when you start working, the mu naught in the numerator, which is expressed as 4 pi by 10 to the negative 7 Tesla meters per ampere. That simplifies the 2 pi in the denominator. And of course here, Tesla is the units. Those are newer for us. Tesla will be the units, the standard SI units for magnetic field intensity. The 2.1 centimeters, of course, you got to go meters on that. All right, we're cranking. I'm up to 8 minutes here. Okay, I think the rest of this is a lot of, and this is what you need to know. Mu naught I over 2 by pi d. For now, that equation, it makes sense based upon what we saw in lab, so I am keeping it within the theme of, enhancing curriculum, not moving forward in curriculum, of course. Sorry, sip of coffee there. It's that equation's a little magical. I mean, you know that more current means more field and farther from the current means weaker field. That's not magical. The exact structure of the equation is, I'm going to teach you, well, I hope to teach you at some point, this thing called Ampere's law. And it is to B fields as Gauss is to E fields. And that's all I'll say. It's a cool thing. Here's neat. Here's something neat. You're going to deal with the B field at the different points in question, A, B, and C. At point B, they're going to either add to 0 or double their effect. So you can get away with doing the math just for one of them as long as the currents are the same. And then either, realizing that you're adding opposites, answer 0, or multiplying the effect of one of them by 2. At A and C, you're going to get diagonal fields, but they're either going to Well, let's just do point A. All right, so the wire up high, I've got an outward current by right-hand rule. So at point A, that field, the field due to the top wire is going to be down and right, actually. In fact, point towards the second wire. Speaking of this, so you got a down right due to the upper wire. Now, let's look at the wire down below. You got an X marks the spot, so we see the back of the arrow. So the field is spinning clockwise around the bottom wire. So at point A, you got an upright. Okay, so I've got two identical magnitude fields at point A. One is upright and one is downright. So I don't even have to mess with the Y components because they cancel. So what I do is figure out the effect of one of the wires, figure out its X component, double it, stick a fork in it, done. All right, so if my interest wanes now, your interest probably waned 5 minutes ago. So again, the rest of these are not too surprising. Oh, you've got A, B, and C. Again, you got to think of it. I see a lot of distance ratios of 1 to 2. I guess what I would say, yeah. So you got two wires making field. The currents are opposite. Just think carefully. The point is this. Opposite currents don't necessarily mean the field cancels. You have to think about the specific point in question and where that point is relative to each current carrying wire. If I'm above a rightward current, but I'm below a leftward current, for example, then that has a different effect than other arrangements. I don't even know. Is there a maximum length of YouTube video I can upload? I guess we'll find out. All right. So this is cool. Nothing is crazy here. Oh, okay. Cockeyed wires in problem 12 in the set. That's okay too. Ooh, capacitors and stuff. Good luck on that one. Ooh, loop to loop. Okay. You're good. I may have missed one as I was scrolling and talking. There was a neat one about, power lines. And there's always a debate of, oh no, there's high voltage power lines running past the school or running through your neighborhood. And is that going to give everybody brain tumors or whatnot? I thought there was one problem where it kind of gave you a scenario like that and asked you to deal with field strength. Now, you and I have no idea, okay, how much field strength is too much field strength for that. But nevertheless, an interesting problem. All right, I'm going to try to upload this to YouTube. We'll see.